Okay, so let's start with chapter 26, which is DC circuits. So Stephen already covered most of this. If you're having a series circuit, then you add up the resistances. If you have them parallel, you do this reciprocal relationship. Just know the equations. We're going to skip this problem for now because we already covered most of it, and that's the answer. Let's talk about Kerkoff's rules for a bit. They're very intuitive. So if you just think about, like, say, a water pipe, the water flowing into a pipe must equal to the water flowing out of a pipe, right? And you can think of water as analogous to electric current. So that's Kerkoff's junction rule. The water flowing in to a node or a junction has to be equal to the current coming out of the node. The next rule is Kerkoff's loop rule, which is that any loop, you go through around any loop, then the voltage around must be zero. And that makes a lot of sense because if you just think about what potential difference is, if you start at one potential difference, you go around a circle and you end at the same point, that means that you're still at the same potential difference, which means that the change in potential difference is zero, right? Does that make sense to everyone? Can everyone hear me? Okay. Okay, cool. Let's do a practice problem for this because you can really learn the best by doing the practice problem. All right, so this is the problem. Let me. Can you guys see the screen, the PowerPoint screen?
Not right now, no.
Steven, oh. I need your help. How do you
share your screen?
No, do the whiteboard.
You go to share screen. Whiteboard.
There we go. I know. Okay, so you guys try to do this problem real quick. This is a pretty simple Kerkoff's rules problem, but you can notice that you can't do this using our previous method of just using resistors and equivalent resistances. You have to use Kerkoff's laws. So it's pretty interesting. Anyways, I'll just go over it a little bit. So first of all, let's look at this loop right here, loop 2. So what we do is, first of all, let's write the loop rule. The loop rule is the sum of the voltage differences across any loop is 0. So the first thing that we do is we define current directions. It doesn't matter that if we're wrong or not, but we need to define them in the very beginning just so that it stays consistent throughout, right? So like we'll define the current direction here to be going like this. And if we get a negative value, that just means simply that the current is going in the opposite direction. But we have to define this direction in the very beginning so that we stay consistent. And it's define this one to be here and define this one to be here. And what this means is also this is where it goes, and this is where it goes, and this is where it goes, and this is where it goes. This is where it comes out, and this is where it comes out. Right? This is just following a loop around. So if we write the loop rule for loop 2, start at A and go around and back to A, you see that, well, first of all, one thing that we really need to understand before anything is the sign conventions. It's actually really important to understand sign conventions because you can probably, if you get the signs wrong, you could get the entire question right, but then you just get the sign wrong and you get it wrong. But these are the sign conventions, memorize it. But basically it's that if you have a voltage difference and you're traveling in the direction, so voltage differences, hold on, let me get my pen. Voltage differences always point, here, let's just draw the point of the voltage difference goes from negative, so this is the negative side of the voltage difference, and this is the positive side of the voltage difference. They always go from negative to positive, okay? And if you're traveling, so let's say that we're traveling in this direction and you're traveling in the opposite direction of this voltage difference, and that's a negative voltage, okay? So we're gonna start off, we're gonna travel in this loop. So we're traveling the opposite direction of the voltage difference. So that means that this is negative, the electromotive force of this, whatever this is. And then we pass through this 1 ohm resistor here, right? So, and all right, so the sign convention for a resistor is different from the sign convention of a electromotive force. How a resistor works is wherever we define this current, if we're going opposite, so if we're traveling opposite to wherever we define this current, then it's positive, right? So in this case, it is positive because we're traveling in this direction. So that means that we're traveling opposite to where we define the current. So that means that we're adding the current times the resistance, which is 1 ohm. So 1 amp times 1 ohm. And then we go around here and then we go right here. So we're traveling in this direction and the resistor is also going, the current is also going in this direction. So that means in this case, the voltage difference is negative in this case. So we'll subtract 3 times 2, which is again, the voltage difference across the resistor. If we remember, is V equals IR, so the resistance times the current is the voltage difference. And then we come back to A. So this entire loop is 0. And this gives us an expression. So like the question say is asking us to find what is the value of this electromotive force and what is the value of, say, this resistance. We just got to keep setting up equations until we get enough linear equations to solve for these unknown variables. In this case, since we have we have 2 unknown variables, we need 1 more equation. And that 1 more equation is going to be loop 3. I think someone has a question, if I'm not mistaken.
It's me.
Oh. Okay. But yeah, so you'll do this exact same thing. The main point here is to remember your sign conventions, okay? I'm gonna move on. How do I get rid of this stuff? Okay. All right, so this is an example of, wait, did I skip a slide? Okay, this is another example of the Kerkoff's rules, but we can just skip that. All right, so ammeters and voltmeters, this is just generally, I don't think you need to know this, but just remember that ammeters are always in series, the resistances must be close to 0, blah, blah, you can read that. Okay, this is gonna be on the test. You just have to memorize these equations, all right? Yeah, I'm not gonna go through how you derive them because you use differential equations, but memorize them and know where it's used. All right, so now we're getting to chapter 27, which is magnetic fields. This is most definitely going to be tested as well. Just like the equation is pretty simple, but the direction of the force is pretty confused often. So just remember the right-hand rule, which there's many ways you can do it. The way I like to do it is the equation is V cross B. So you point your index finger at V, and then you point your middle finger at B, and then wherever your thumb goes is the magnetic field direction. You can also do it a way where you point your entire hand at V and then you cross your fingers in the direction of B, and then whatever your thumb points, that's the direction of the force. And also you have to remember that if you're talking about electrons, whatever force you get, flip it around, and that's an electron. So here's an example problem. You can work through that on your own time. Here's the answer to that problem. This is just applying this equation. And finally, the last thing he wanted to talk about was cyclotron frequency. It's actually not very well covered in the book, but basically what it means is you have a cyclotron. Let me try to draw this out. Come on, what's going on? Nope. Anyways, you have a cyclotron, and what a cyclotron does basically is just like a circle, or like a circular accelerator. It accelerates an electron around in a circle. And the reason why it's so useful is because the frequency doesn't depend on how fast the electron is. And that's really important because you can imagine as the electron's going faster and faster, you want to have the same frequency so that you can apply the same voltage on it and accelerate it each time. So the main thing to remember is that the cyclotron frequency, this is the equation for the cyclotron frequency, and notice that it does not depend on the velocity of the particle. And you see the magnetic force, on the other hand, does depend on the velocity of the particle. So there is a derivation for this, and it's actually not that hard to do, so I suggest that you look at it, but it cancels out in the derivation, and you end up with this equation for the cyclotron frequency, which is the charge of whatever you're accelerating times the magnetic field divided by 2 pi times the mass of the particle of whatever you're accelerating.
Can you explain real quick?
You guys have any questions about any of this stuff? I think that's, I just kind of based it off of the picture that PHYS said was going to be on the test. I didn't go into any details about anything.
Can you explain real quick what cyclotron frequency actually is?
Cover more in detail.
Is there like a practice problem from Expert TA that we did that had to do with this? Or?
Yeah, and it's the mass of the particle that you're accelerating. No, Donovan, I think you're muted. Let me unmute you. What the? Okay.
Okay, I tried to unmute myself, but apparently that didn't work.
Oh wait, hold on. It's my sound is not on. Sorry guys, I didn't hear anything this whole time. All right. Could you? Yeah, now I can hear you.
Okay, can you explain real quick what cyclotron frequency actually is? Because the book doesn't seem to mention that very well.
Sure. Okay. So frequency. Do you guys remember what frequency is?
Yeah.
Like if I say so if I'm spinning a ball around in a circle and I say the frequency is 5 hertz, what does that mean?
It's going around 5 times per second.
5 times every second, right? And just to clarify, what is the period then? If I say that the frequency is 5 hertz.
Seconds per rotation.
Say that again, sorry.
Seconds per revolution.
Yeah, so that would be 1/5, right?
Mm-hmm.
So it would be 0.2 seconds per revolution. And this is the exact same definition of frequency in this case. So you have an electron that's going around in a circle, right? And the cyclotron frequency is how many revolutions does it make per second? Okay, so and how you calculate it is, actually, I'm not gonna go into how you calculate it, but yeah, that's just what it means. However many revolutions it goes around in a second. Does that answer your question, Donovan?
Yeah, I got it.
I was just wondering, is there, like, you don't have to do a problem with us, but is there a problem we were assigned that has to do with this?
Cyclotron frequency. I didn't include a problem on purpose because I think it's just going to be straight up plugging in. I mean, there's nothing that you can ask besides, what is the cyclotron frequency?
Gotcha.
So I wouldn't worry about it. Just memorize the equation and what it means. I guess the only other thing they could ask you is like, what is the period of the rotation? You just have to remember like, what is the relationship between period and frequency? Do you guys know what it is? Period is 1/frequency, right? Also might ask you like, what is the angular frequency? I don't know. I don't think it's going to ask you that because this is not really, this is more mechanics. You're just converting between angular frequency and frequency. So yeah, I think it's just going to ask you to straight up plug in the numbers.
Thank you.
Yep, no problem. I think maybe the one thing that would be like not plugging in numbers is Kerkoff's laws. You can't like do the same thing over and over for them because you have to like create new equations for them. So just the main thing is doing practice problems for them. Okay, anything else? Okay.
There's gonna be stuff about torques on loops and also the relationship between resistivity and resistance. That's a lot to cover, but you don't have to do that if you don't want to.
I think resistivity is just a formula, but can we go over torques real quick?
Yeah, sure. Okay, I can do that. Sure. Okay, yeah. Well, I'll cover resistivity as well. It's not too much.
Okay. Also, sorry. One more. He mentioned specifically like a copper tube resistivity. I don't know if that helps or anything like that. That's just something.
Well, that's just a constant that you would have to, I guess, be given, right?
Resistivity is a constant dependent on the material, right? Yeah, you're right.
Yeah.
What did you say, Stephen?
This is my slide. I have the equation for resistivity of a wire.
Oh yeah, Stephen apparently has the equation for the resistivity of a wire. It's where is it?
Is it any different because it's a tube? Like there's no inside.
You mean the resistance? Is the equation for the resistance different?
Yeah.
You just have to use the area of the tube. So like you're saying it's hollow?
Yeah, I'm pretty sure.
Okay, yeah, so like then in the equation, when you divide by the area, you're dividing by the cross-sectional area, and the cross-sectional area does not include the hollow part. So what you would do is if you're given the outer radius and the inner radius of the tube, you would take the area of the outer radius and subtract the area of the inner radius, and that's the cross-sectional area.
And you said this is for a hollow tube, right?
Yeah, so like,
But
yeah.
in general, it'll probably be not a hollow, but like, yeah, that's just basically finding the area of whatever you have, the cross-sectional. Yeah.
Yeah, just the cross-sectional.
Okay.
That's
All
all.
right, cool.
Yeah. But yeah, this equation is just something you gotta memorize. Not much else to say. So does that answer everything that you said? I mean, all your questions about resistance and resistivity?
Yeah.
Okay, cool.
One more quick thing related to resistance.
Mm-hmm.
So you know that resistance and temperature equation,
You don't need
where it's like,
yeah, I'm pretty sure you don't need to know
is
that. But I mean, I would
resistivity
write
or is
down.
that resistance?
Say again?
Is that the temperature equation resistivity or resistance?
Well, let me ask you this: if you have a wire and you're heating it up, does the length and the cross-sectional area change?
No.
So what does that mean? That means that that equation also applies for the resistivity. It applies for both resistance.
Okay.
Because you can just
Gotcha.
plug it in. You can just multiply both sides by area divided by length, and then it'll just turn into resistivity, right?
Oh, okay, makes sense. Okay, cool.
Okay, and the other thing was the torque on a current loop. So yeah, I'll cover that as well. How do I, Steven? I don't know why I'm such a boomer. Come here. How do I do a whiteboard?
Oh my god, I literally showed you. You do new share, whiteboard, share. I just did.
Okay, can everyone see this whiteboard? Okay, so this is, I'm about to cover the current on a, what the heck? Current on a, no, force on, torque on a current loop. Okay, yeah, that's it. So first of all, what is the equation for the force on a current loop? Not torque on a current loop, but force on a current loop. So say there's a current I going this direction, and then there's a magnetic field going out the page. If you guys remember, do you guys remember what's the equation for the force on a current?
Isn't it F equals ILB sine theta?
Yeah, or I'll just write I cross B because that's the exact same thing that you're saying. It's also equal to LIB sine theta. By using cross product tells you what direction you're gonna go.
Mm-hmm.
So yeah, the main thing now is to know exactly where this force is going. There's a practice problem that Emily gave me, which is I think a really good problem. If you have so say you have a current loop like this. All right, and you say that there's current going around the loop like this, okay? Actually, here, let me first of all. Oh man, I drew this. Here, let me draw it again. You have the current loop actually pointing a bit off center from the z-axis. So this is the x-axis, this is the y-axis, the axis. And say that the current is going here, and going here, okay? So now the question is asking for what is the torque on this current loop? Well, all you need to do is just apply this formula right here and realize the directions that the forces are going. So let's first talk about the force on this bottom wire right here.
Is there a magnetic field?
Yeah, let me define the magnetic field, you're right. The magnetic field just points in the x direction, so pointing in the negative x direction, that's the magnetic field.
Okay. Can't you just use the formula? Like, isn't it just a plug and chug like question? Like,
but it's
equals NIAB sine theta.
Okay, but I'm asking for the torque. That gives you the force. But what's,
yeah, the torque is NIAB sine theta.
What's N?
So like that's like the wasn't that like the direction? Like it's like your what's it called? I forgot what it's how Perez described it. It's like the what's it called? I can just look it up, but I forgot what it like how Perez called it. Hold on.
That's fine. But I don't think this question is a plug and chug. Because
N is the number of turns, so in this case it'd be 1.
Oh, okay, yeah, but that's not the. That's actually yeah. I mean, the equation that you said is right, but what we're talking about here is a bit different. Like the question is asking what is the torque along this axis, along the y-axis.
Oh, so it's not down the middle.
No, it's down the y-axis, along the y-axis. So say that it's pivoted right here.
So is there still like a current going down the y-axis or no?
No, there's no current going down the y-axis, but there is a current going here.
Oh, okay, cool.
Wait, so this is, I think this is a bit different than what you're asking. What you're asking is like from the textbook, where they just like give you a current. I think what you're asking is if you have a current loops like this, and then there's a magnetic field pointing at it, right? And then this current loop is spinning around like that. Yeah, if you have that, then you just plug and chug using the equation, right? Hello?
Yeah.
I think this is what you're talking about. But this equation, actually, you can't plug and chug because there's not a singular equation how this works.
Sorry to interrupt real quick. So for the thing you just crossed out that Tanner was mentioning, what was the equation for that again?
You can look in the textbook. I don't have it memorized.
Okay.
Let's see. Oh boy.
Tanner, do you remember by any chance?
Yeah, it's torque equals NIAB sine theta, and N is the number of turns.
Oh, okay,
I is the current, and A is the like area of the loop, and you have to use the direction of the. It's like you take that area and you take the vector of that area, like wherever direction it's facing, and you cross that with the field.
Okay, got you. All right, cool. Thank you.
You said that this is the torque?
Yeah, but it's A cross B, not I cross B.
Oh, that makes sense.
I don't know if that. Yeah, I think it does matter. I think it has to be A.
It does matter. It tells you the direction. The area, by the way, is whatever is perpendicular to the area of the loop.
Mm-hmm.
Yeah. But just remember those equations. I'm not going to cover them because they're just something that you remember. But this equation or this question right here, you can't really remember it. It's more thinking, and you have to actually use this equation. So I'll cover it real quick. But basically, let's first talk about the torque for the force on this side. What is the force on this side? Well, let's use the right-hand rule. The force, the current is going this way towards the z-axis, which is me, and then
the Hall effect.
Is
this the same thing as the Hall effect?
The Hall effect is much different than this.
Okay. The Hall effect's not covered on the test.
Yeah,
that's what I was asking.
I don't know if this is all covered on the test either. This wasn't on the sheet that was sent on the group chat, but someone I think Tanner, you said that they're covering torque on current loops on the test.
Yeah, I'm almost positive they are.
Yeah, I'm pretty sure they mean this formula, but this is also a valid question you can ask for the torque on a current loop. But basically, let's think about what directions the magnetic force is on this side of the wire. So the current is pointing in this direction, and then the magnetic field is pointing in this direction, so it's going down, right? Now, tell me what's the magnetic force on this upper part of the loop?
It's up.
Yeah, and it's also the exact same current, because we're saying there's the same current going through this entire place. So that means that the two forces cancel on up and bottom. So that means that only this guy creates a force, right? So then you would use the right-hand rule again. So what you see is that the force on this loop points directly in the directly in the z-axis, okay? And this actually creates a torque because this wire loop is not directly aligned along the z-axis. So if we look at it from above, then it looks like this. So this is the z-axis, and this is the x-axis, and this is the current loop looked at from above, and then this is the force of the magnetic field, right? So this actually produces a torque in this direction, and that torque is just basically the magnetic force times sine theta, and that's how you would find the torque on such a problem like this, right? So you're just using this equation.
So how is that different from the NIAB sine theta one?
Well, how do you plug in NIAB sine theta for this?
So like the number of turns in this would just be 1, so N pretty much just disappears.
Also, another thing is that there's no currents going through this wire right here.
How is it different at all if it's not a complete loop?
You can imagine like it's being connected by something on the outside. Like that doesn't really matter. Just know that the current only goes through 3 sides.
So like there's like not even a side on the other part?
Well, there is a side.
It's like, but it's not a conductor, or it's like it's not carrying a current.
Yeah.
Is it able to rotate at all, or that doesn't really?
That's the pivot. So it rotates around this pivot. Yeah. So this problem is a lot different than this problem because you can't just plug in the equation here. You have to actually think about what this equation means and then find the torque. But don't worry about this equation because I don't think he's going to test it. But do memorize the equation that Tanner was talking about. I think that's going to be on the test. Okay. Is there any questions about anything?
No, you did a good job. Oh wait, also for the cyclotron thing, I think one of the things he's going to talk about on the test is just the circular motion of like electrons and protons in a magnetic field, and just how you have to know like if a proton, which direction a proton will rotate, and then which direction an electron will go in, something like that.
Okay, yeah, we can just go over that in like 5 seconds.
Yeah.
How do you know what direction a proton will rotate? You can memorize it or you could figure it out. What the heck? How do I draw stuff? Well, anyways, if you think about, oh my gosh, I need to draw stuff. Steven, come over here. Actually, no, I got you. I got it. Never mind. I'm being stupid. Okay. What the heck? Never mind. Okay, never mind. All right, I got it. So, say the magnetic field is pointing out the screen. Okay. You have a proton moving in this direction. Okay. Then you just apply the right-hand rule, right? So what direction will it go? Well, let's point our index finger in the direction of the velocity, and then magnetic field is going out of the page. This is a very weird angle, but so I'm pointing towards myself. That means my thumb is pointing downwards. So there's a downwards force right here. And then if you draw it here, there's still the same downwards force. So then it goes around in a circle like this. That's how you would figure it out. You just use the right-hand rule all the time. So just check yourself. It just goes around in a circle like that. So that means that it goes around in a circle clockwise. On the other hand, electrons just go in the other direction.
My phone like froze up. Can you repeat this again? Sorry.
So yeah, protons go in clockwise, and how you will figure it out is just by using the right-hand rule a lot of times, the velocity times the magnetic field, and just follow where your thumb points, and your thumb is always pointing towards the center of the circle. So
Okay.
it rotates clockwise, and electrons just go in the opposite directions. So electron go counterclockwise. If you don't want to reverse direction, the other thing you can do is use your left hand. So for negative charges, you do the left hand rule. For positive charges, you do the right hand rule.
Gotcha. Thank you.
Any more questions?
So just confirming, protons always go clockwise and electrons always go counterclockwise?
All right, so if the magnetic field is pointing out of the screen. Now let's talk about the magnetic field.
Okay.
I would just memorize how to, I wouldn't memorize it, I would just know how it's derived. If it's going into the screen, it's reversed. Because then your middle finger is pointing into the screen. So say a proton is moving in this direction, then the magnetic field is pointing down into the screen. So that means that the force is pointing upwards. So that means that it goes around in a circle like this, which means that it's actually going counterclockwise. And then electrons go in the opposite direction. So electrons now go clockwise.
Pretty much, just know the right-hand rule, and then if it's an electron, then you're basically going to go the opposite of whatever you got if it was a proton, like it's the opposite direction. And
Right.
if there's no velocity at all, then it's not going to move.
Right.
So it has to have initial velocity.
Right. Yeah. Yeah. I'm not going to go much more in detail, but yeah. Okay. Anything else?
No, I think we covered everything.
Yeah. There's a lot to study, but I think Dr. Press will make it easy. So don't worry so much, and y'all are very prepared. So be confident in yourself. I think the main thing to look out for in terms of stupid errors is electrons versus positrons. Oh my gosh, electrons versus protons. So like just be careful in the question you're reading. If it says electron, always reverse whatever direction you're talking about with your right hand rule. Or if you want to avoid that step, just use your left hand.
Oh, I don't want to make this drag on forever, but like we don't have to go over it. Just like also just be prepared, because there's also going to be like you have to find how long it takes for a capacitor to charge.
Yeah,
that's just that formula.
Yeah.
That's just, I just like went over it very, very, very quickly because it's something that you memorize. So
yeah, and if you have your algebra down, you're fine.
Yeah.
Yeah, so you just plug it in. Another thing, just remember what the time constant is. It's just RC. It's kind of easy to remember because it's called an RC circuit.
And RC is just resistance times your capacitance, right?
Yeah.
Should be very easy, so do not worry.
All right.
We are allowed to calculate a rate?
Probably. We definitely have to be one for us to calculate stuff.
Wait, I'm sorry if we're running out of time, but could you like explain what's on the page one last time? Because I still don't really get it.
Explain what's on the what?
Like what's on the screen right now?
RC circuit charging.
No, the protons
Talking
go
about like the magnetic field, like an electron in a magnetic field.
Oh wait, y'all on the whiteboard still?
Yeah.
Oh, okay. I thought
pretty much just
yeah. So I don't know, for some reason my hands just like don't lead me to the right answer, I guess.
Wait, Can you say that again? I didn't hear you.
Oh, can you just like briefly explain these two one last time, like using your hands, like using
Yeah,
your right
okay,
hand?
sure. You have to use your hand as well because it might be mirrored on my screen, so I don't know if it's the same direction for you. But all right, so let's consider this case first with a magnetic field pointing out of the screen. Remember, dots means that it's pointing out of the screen, crosses means it's pointing into the screen. Point your index finger in the direction of the proton. Okay, so that's to the right of the screen, right?
Yeah.
And then point the magnetic field towards your face, so your face is out of the screen. And what do you see? You see that your thumb points downwards, right?
Oh, does it?
Does your thumb, so if you point your index finger towards the right and you point your thumb towards your face, and that means your thumb goes down.
Yeah, yeah, I see now.
And then because that's like a centripetal force, right? It's like a ball being tied to a string being spun around the string. So then it goes to a position in a circle right here. And if you do the exact same thing with your right hand rule, you point your thumb point your index finger in the direction of where the middle finger towards your face. You see that the direction of the magnetic field is still going towards the center of the circle. So that means it goes in the center of a circle in this direction. And you see that this direction is.
Yeah, okay. I just got it. Thank you so much.
Yep, no problem. Okay. Any last questions?
Nothing at the moment, but are you available like a little before the test tomorrow, just in case?
Probably, yeah. I think Shar will also be available, and he might host another review session, but I don't think that's necessary. I think we'll just be.
Yeah, I think I'm done going over big reviews, but just in case I have a small question or anything.
We'll be there. You can just text.
All right, great. Thank you.
Okay, yeah. So this meeting's about to end anyways, but yeah, y'all are gonna do fine. Do not worry too much. If you have any more questions, just ask me. But I'll just end the meeting right here. Okay. Goodbye, everyone. I heard record the first one.